My name is Dr. Shobhusha Chishen. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bouquet is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that you'll be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we'll be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen. Hello and welcome to 20th class of my course on Physics 2. And today actually we'll be shifting from our entire discussion of whatever you have been doing with quantum mechanics and its application in quantum computation. Now we actually focus more on the materials aspect. Okay, we'll talk about a material, okay, which you can only explain with your quantum ideas. And these materials are very special kind of materials, which is beyond those metal insulators and semiconductor that you know from your solid state physics courses or basic electronics courses. We'll be talking about some special materials which are essentially made directly from atoms and molecules, and in general they are called nanomaterials. Okay, so you'll be now introduced to the world of nano, the nanoelectronics. And it's a vast topic actually. The entire science, it has got its own nano version. The physical science, physical science means whatever you see, okay, all the physical properties, suppose electrical property, thermal property, mechanical property, optical property, almost everything gets changed, okay, in the when the material side becomes very less, okay. Chemical properties also get changed. And as a job of a technocrat, your job will be to make use of the change in the feature, okay, happening at the low dimension for the purpose of human being. So what shall we do now? My job is to now introduce you with the world of nanomaterials. We'll be talking about what are nanomaterials. The modus operandi of the discussion would be that I'll be talking about what is nano and what are nanomaterials, what are the examples of nanomaterials, what is the speciality of these nanomaterials, that is, what is the need of studying them separately, okay, that has to be clarified. And then classifications of these nanomaterials. And if you understand this, you will automatically, some of the essential applications of them will come up. But mind it, each property, each application has its own branch, okay. They are studied separately, okay, but you'll be only introduce some of the basics of it. So we'll only focus on the primarily what is called nanomaterials. So this is me. Now you see, just get to know this person, okay, with the hands up, okay. This is not that usual hands up, okay. It is, he is very happy with that expression. He is Richard Feynman, one of the greatest physicians of the previous century. Okay, now Richard Feynman has got a seminar lecture, okay, there he told, uttered a word called, there is plenty of room at the bottom. Bottom means at the very low dimension. So it was thought long back in 1959, as you can see, is one of the lectures. So now it is 2020. So in last 20 years, there has been a nano boom. So basically, whatever he thought, the pioneering scientist thought, he was a theoretician, he thought, and what theory tells, what theory sees, what theory can foresee, I should say, experiment realizes it after some time, okay. So it has taken some time to experimentally gather all these things, prove experimentally, to design experimentally all these things. But long back in 1959, Richard Feynman told it, okay, that this wonderful concept, okay, that is, there is plenty of room and lot of options of there, new science, new technologies waiting there at the dimension, very low dimension, and that is nanotechnology, that is nanomaterials, okay. So now the word nano, it's basically, it means dwarf in Latin, okay, it's a Latin word, means dwarf. Dwarf means short, okay, something which is, so it talks about dimension, it talks about length scale, okay. So when we talk about nanomaterials, so it's essentially focus on length of the materials, length means size of the material, I should say, okay. So it's a material of very special size or something very specific size, and material, you understand, is related to the matter. So the entire concept of nanomaterial came up about the something related to the size of the materials. So if the material size becomes special, something in some special range, then it is called a nanomaterials, okay. So now to realize it, to discuss it, okay, now let me give some example how matters do vary according to length scale. I request you to understand this change that I'll be, you just walk with me. I'll walk from the very small dimension to very large dimension. You will see how the world gets changed. It's very funny, very fascinating, very interesting. You will realize, okay. So let us study it. First, we start with our very famous water molecule. Water is a molecule, and the size, of this water molecule is this much, okay. It's 0.1 nanometer. So 1 nanometer, as you know, is 10 to the power minus 9 meter. So 0.1 means 10 to the power minus 10 meter, which is angstrom. And molecular range is angstrom range, okay, that is less than a nanometer. Understand? Now you move from this molecule to water to a slightly larger molecule, okay, which is fullerene. The closed diameter of the fullerene, these are like balls, buckyball fullerene, they call it. Size of them is close to 1 nanometer. So we are approaching nanometer range. So now, after that, I move to DNA molecule. This is another molecule. So just look at the examples I'm choosing. I'm not choosing any big element. I'm choosing some molecules for our example. So we started with water. whose dimension is tenths of nanometer. After that, I get close to nanometer, that is fullerene molecule. Now my example is DNA. The length of DNA is 3.4 nanometer, so I am above 1 nanometer, but less than 10 nanometer. And the width you can see is also, it is not very high, okay. So its length scale, it is above 1 nanometer, okay. So DNA is another classical example, but it's another molecule, okay. So dimension is falling between 1 to 10 nanometer. From DNA, this is another allotrope of carbon, just like fullerene ball was carbon allotrope. This is called carbon nanotube, okay. Carbon has got three popular allotropes: carbon nanotube, graphene, and the fullerene ball. So they have got tremendous importance in respect of the nanotechnology, okay. So you see, carbon nanotube, maybe single wall, maybe multi wall, we will discuss it later on. So its dimension, the diameter may be varying from 2 nanometer to 25 nanometer, that multi wall carbon nanotube. So we are now going above 10 nanometer, okay. So now this is few more examples, okay. The gold nanoparticle, the sizes are close to 10 nanometer, okay. The gold nanoparticle, you can see, it's a beautiful example. You see how the size of the gold nanometer particle is changing: 20 nanometer, 30 nanometer, 40 nanometer, 60 nanometer. And you look at those, how the colors are changing. This is giving you a signal. As the size is changing, property is changing. Which property? Optical, because color is changing. So we'll discuss it again. It will come up in our discussion. But now we are living from 20 to 60 nanometer, okay. So these are the gold nanoparticles, they call it, cluster of gold atoms. Now this is coronavirus, okay. So basically you see its dimension is close to 100 nanometer, okay. So I have started from water molecule, which is tenths of nanometer. After that, is taken up the example of fullerene ball, which is close to 1 nanometer. Then between 1 to 10 DNA. Between above 10 nanometer, we have got the example of another nanomaterial, okay. There is our 25 to 30, 2 to 25 nanometer is the carbon nanotube. And after that, I get all the examples of the gold nanoparticles of various size. And now this is 100 nanometer is the virus, okay. So these are all falling their dimension. If you start from fullerene itself, they are all falling between 1 to 100 nanometer. Mind it, 1 to 100 nanometer is going to be the key word for our discussion, okay. Keep this range in mind. Actually, all material whose dimension falls between 1 to 100 nanometer is called a nanomaterial, okay. If you know, any material has got three dimensions, you may say in rectangular way, length, breadth, and width. So if one of the three dimensions, for example, any material, okay, suppose this pen, it has got it has got a length, it has got a cross section. If the length or cross section, one of them, the cross section means two of the coordinates are same. So basically, if one of the coordinate is falling in the length range of nanomaterials or nanoscale between 1 to 100 nanometer, then it is to be called a nanomaterial. If I now go, just let me complete the length scale. This is the E. coli bacteria. Its dimension is, you see, it is above 100 nanometer. Okay, it is 3 micrometer. 3 micrometer means I have now crossed nano range. 100 nanometer, now I am going into 3000 nanometer. Thousands of nanometer. 1000 nanometer means 1 micron. So this is 3 micron. And now this is, say, cancerous cell. Okay, cancer cell is like 15 micrometer. Okay, so 15,000 nanometer. So I have crossed, I am not no more between 1 to 100, mind it. And 15 micrometer means you can see this through microscopes. So that's why you can see a bacteria, E. coli bacteria through microscope, normal microscope, optical microscopes. And cancerous cell can also be seen because its range is between 15 micrometers. So micrometer scale microscopes are available. Okay, usually microscope's job is to see this, only resolution has to be controlled properly. Now this is the tip of a pencil. The tip of a pencil is like 0.7 millimeter. 0.7 millimeter means you are getting into now into 10 to the power 5 nanometer. The micro range, it was 10 to the power 3 nanometer. Now you are into 10 to the power 5, and you can see, all of us can see the tip of a pencil with our naked eye. So tenths of a millimeter is the range, or 10 to the power 5 nanometer. So we are now slowly moving into the visible range. Okay, the what our naked eye can see. This is a tennis ball, which is of few centimeters. Okay, so that means if you put in a nanometer scale, 10 to the power 7 nanometer. So this is the entire length scale. Now, only in our discussion of nanomaterials, we'll be only focusing on all the examples I have given between 1 to 100 nanometer. It started with my fullerene. Next example was DNA, from DNA to carbon nanotube to gold nanoparticles. Okay, I ended up with, with the virus. Okay, but any material whose dimension falling between 1 to 100 nanometer is called a nanomaterial. Not all the dimension, at least one of the three dimensions. If all three are in the nano range, that is also very good news. But if one of the three dimensions are falling in the 1 to 100 nanometer range, that is going to be called a nanomaterial. And nano range means 1 to 100 nanometer. Okay, so it's a very popular examination MCQ question. What is nano range? It is 1 to 100 nanometer. Any material whose one of the three dimensions in the nano range is called a nanomaterial. I request you to go through that YouTube video. I've given the link. It will talk about the lens. Now look at some of the, now what you see, you will see very soon. I will make a short journey how the property of the material or the feature of the material changes the moment you enter the nano dimension, enter into the small dimension. Unique physical property which is available in the large scale, in the macroscopic scale, will be completely modified, will have a drastic change. Okay, if you enter into the nano range. Okay, based on that, if you could manipulate, if you could control those change in the property of the material the moment you nano range, then you can develop nanotechnology. Now, nanotechnology is the most modern technology. It will be sustaining for years now. So there, your job is to control at everything at the atomic and molecular scale. Now, it has got tremendous application in every sectors of our life. I'll go to the application after some time. Now, before that, you see, these are some popular examples of the nanomaterial. One of them, you can see the animation. Okay, that is not, okay, that is a robot basically. Okay, that is called a nanobot. Nanobots are used in the medical for surgery purpose. Okay, the size of the nanobot is very low. It is in the between 100, less than 100 nanometer. So you can see you can see there, it will work there. It will be moving into the blood vessel. It can clean some of the clots there, etc., etc. And the other one, the top one, is that the nano drug delivery system. It is doing the job of targeted drug delivery. It is directly killing the cancerous cell. Okay, so these are all okay. You can see simulated environment created. Okay, the cancerous cell is now, you can see there nanomolecular drugs are going, and it is actually killing those cancerous cells. Okay, only the cancerous cells is hitting. It is not affecting the other parts of the body. Please see the animation very carefully. So those nano drugs are there, are molecular drugs. The actual drug, actual toxic material is coated with nanomaterial. Okay, so it will only go to the cancerous part of the body, marked in green there in the picture, and it will kill it. Okay, and red one is the normal body parts. Main problem with the old cancerous treatment is that it kills a lot of good body cells also. So that is not going to happen if you use the molecules coated with the nanomaterials. Okay, so these are some of the popular application in the medical technologies, but we'll be only mainly focusing on the electronics part of it in our course. Okay, now this is just same story. Okay, we started with water, okay, whose dimension is less than a nanometer. Okay, after that, so many examples I have given. It may be the fullerene ball, it may be the DNA itself, DNA, RNA, okay, the carbon nanotube, the gold nanoparticles, okay, all these are falling into the 1 to 100 nanometer range. So all of them are examples of nanomaterial. Okay, the bacteria, obviously not beyond this. Bacteria is in the micrometer range. These are some more popular examples of the nanomaterials. Okay, now that ball is the fullerene ball, whose dimension is close to, the diameter is close to a nanometer. That green one is the carbon nanotube. I just told you it's diameter of the ring of the cylinder falls between 2 to 25 nanometer. The graphene sheet is there, whose thickness is falling in the nano range. And if you keep many graphene sheet stacks, you make a graphite. Okay, we'll discuss the graphene sheet in length. Fullerene, dendrimer, okay, gold nanoparticle, metal oxide. You see so many other examples are there. But we'll be more focusing on the carbon the nanomaterials based on the carbon allotropes when you classify the nanomaterials. Okay, so it's a world. And you know, these are a Nobel Prize winning concept. 2D graphene. Graphene has got Nobel Prize in chemistry in 2012. Okay, it's got tremendous application in every sectors of life now. We'll talk some of them, why it is so special. Graphene has got no band gap. Okay, it's zero band gap. Okay, it is called a semi-metal. So many intriguing features are there, which as an engineer you have to make use of it and do something. Okay. Now, question is that why you have to study the nanomaterial separately? The answer is very simple. If you enter into the nano range, the property of the material drastically changes. There is a huge and drastic change in the property of the material. Now, we'll be mainly focusing on the physical property. Chemical properties also get both physical and chemical property of the both physics and chemistry of the material gets changed. Okay, the physical property gets changed actually. You can see, then what does it mean by physical property? Say gold is a popular nanoparticle. Gold nanoparticles example I have given. Now let me consider how the physics of the material gets changed the moment you enter into the nano range. Now gold nanoparticles, you see, if you see the ball gold, okay, ball gold, what is the color of the ball gold? Yellowish. Okay, so it is the optical property. Gold is a very good conductor, electrical property and thermal property. It's non-magnetic, it's a perfect, it's diamagnetic. Okay, so it is a magnetic property. Its mechanical Young's modulus is of the order of 10 to the power 9 plus 9 Newton per meter square. So it is its mechanical property. Now the observation is that, so the moment you get into nano range, okay, how do you get nano range? There are a variety of methods. One of them is you cut into pieces. That is called, you can go from the top higher dimension to smaller dimension. Variety of methods are there. Mechanical techniques like ball milling, etc., available. The other salt gel, etc. Chemical techniques are also available. Many techniques are there. I'm not focusing into that issue now. Okay, there is more chemical part. We are focusing on physical part. You see, these are all gold nanoparticles. Okay, I have discussed earlier also. Gold is yellowish. Okay, in the normal bulk gold, but if you get nanoparticles of gold, suppose the red one is 20 nanometers size, the slightly orangey, you see, it is 30 nanometers size, slightly magenta color is 40 nanometers size, slightly bluish color, it is a 60 nanometer size. So it's just try to imagine, will it happen ever? Suppose I piece the normal gold into pieces and its color will vary, nobody will purchase it then. Okay, so if you get into the nano range, the nanoparticles of gold, or the class, these is a cluster of balls of gold, okay, cluster of gold atoms, their color changes. So this is one of the features that is happening at the low dimension, which is unlike to the classical way of thinking. Okay, so property gets changed. Okay, physical magnetic property can also change. Look at the gold again. Gold's atomic configuration I presented here. Gold has got one 5s1 electron. Okay, you can see there is an unpaired electron is there. Now ball gold is non-magnetic. Now if you make a chain of gold atoms, okay, that, so you have got a lot of unpaired spin of electrons, okay, kept parallel to each other, chain of gold atoms. Okay, a lot of unpaired spin of electrons are kept. Now you make a, so it's an atomic chain of gold atoms. You get an atomic chain of gold atoms. Okay, you make an atomic chain of gold atoms. This is not bulk gold. This is atomic chain of gold atoms. So now you get a magnetic chain, spin chain. So it can show magnetic property. Now experimentally that change in color you all observe. Now this is just a prediction. Okay, it can be magnetic. Okay, you can see that gold can show magnetic property. It can show magnetic property. So what I'm trying to tell you, the moment you get from the bulk size to nano size, you see physical properties are getting changed. The gold is changing its color, optical property gets changed, magnetic property gets changed. Okay. Another one is that you see main problem is not problem, I should say. The moment you go from the large size to small size, your basic electronic band structure gets no more. I can use band theory because I am now only talking about a few atoms and molecules. So their energy levels are more important. Okay, you can see in the picture also as you go from large size to solid structure to large structure to small structure. So more energy levels are getting, individual energy levels are important. So the concept high energy band formation, interaction with the neighboring electron, etc., etc., those effects are coming in a different way maybe. So individual energy levels are important, and at this low dimension, quantum mechanics is very dominant. The effects of quantum mechanics, the ideas of superposition, the quantum interference of electron waves, all these things takes place. So that's why many new and intriguing physical property emerges. And another very important and directly understandable idea is that suppose another, you see what happened, the surface to volume ratio of the nanomaterial gets changed. Actually, it increases. So let me just explain you what does it mean by surface to volume ratio. Okay, you look at these pictures, I will explain it. Okay, look at this picture. What does it mean by surface to volume ratio? Okay, because surface to volume ratio gets high, very high. So what it does, actually the nanomaterials become super active, okay, hyperactive with the nature. So it's physical, it results in the physical change in the physical and chemical property. I'll just show you with a small calculation how surface to volume ratio gets changed, okay, how it controls, okay. Please see how it changes. It's a cube. All three dimensions are 2 nanometer. Right. The length, all three dimensions are 2 nanometer. All are 2 nanometer. Okay. So what is the volume, surface to volume ratio? Volume is obviously 2 into 2 into 2. And any surface area you choose, it is basically 2 into 2. How many surfaces are there? 6. So basically 2 into 2 into 4 is 6. So it is 6, 4 into 6 is 24 and it is 8. So it is 3:1. So for this case, surface to volume ratio is 3:1. Now suppose I cut into pieces. Okay. Suppose I cut it. Suppose I cut it. Okay, I just cut it from here. Okay, half size I cut it. So if I cut it here, so I'll get how many cubes? I'll get this much. So this is my initial cube. I cut into pieces. Okay, I cut it here. I cut this into pieces. So I'll get some smaller cubes like this. Suppose this is one cube. Each cube having dimension 1 by 1 nanometer. Okay, this is 1 nanometer by 1 nanometer. This is another cube. This is another cube. So this is top 4. This is this part I have covered. From bottom also I'll get 4 more. So 8 is there. So now I want to again calculate the surface to volume ratio. So what is the surface area of 1 cube? 1 into 1. How many faces it has got? 6. Understand? Now how many cubes I have got? So this is 1 cube. That is that calculation I have done. And these are the faces which are exposed to the nature. Now not just this face, for the other, because I have cut into pieces, these faces which was earlier inside, now it is open. These faces which was earlier inside, these faces which was earlier inside, these are open. So I have to consider the contribution of each and every cube. So altogether I have got 8 cubes. And the total volume of the 1 cube is 1 into 1 into 1. And I have got 8 cube. So this is altogether is 48 by 6. 40, ratio, it is 6:1. So in the first case, the surface to volume ratio was 3:1. Now it is 6:1. So mind it. So that means if I look at it, if I present it in a comparative way, this is the larger cube of dimension 2 by 2 by 2. Its surface to volume ratio I calculated is 3:1 because only these faces are exposed to the nature. And if I get into pieces, if I cut into pieces, okay, of dimension 8 cubes of dimension 1 by 1 by 1, so like this, so it's smaller cubes I have cut into pieces. Okay, this is now cut into pieces. So I've got a lot of small cubes are there. Okay, so surface to volume ratio of the smaller cubes are basically 6:1. So you can see as you get into small pieces, these inert surfaces, these are the smaller cubes. So what happens? The inert surfaces are being exposed to the nature now. So the probability of interacting with the nature is more. Okay, now more and more surfaces are exposed to the nature. So it is interacting more with the nature. These are all exposed to the nature. It is interacting more with the nature. So as a result of that, the physical change in the physical property is more expected. Okay, so that's why in the nano dimension, the surface to volume ratio is very high. Okay, as more nano, suppose if I make it to out of 16 pieces, okay, each of have dimension half, okay, half nanometer, then obviously surface to volume ratio will be more. So if you get into smaller dimension, surface to volume ratio rises, interaction with the physical nature increases, and physical property gets changes. So as a result, overall physical and chemical property changes. So what you wrote is, as we approach nano dimension, there is a change in the physical and chemical property of the system. So that's why it is necessary to study that separately. So now we will be talking more about nanomaterials, but not now, because wait a bit, we will talk about the classification of nanomaterials. The sound sources you must go.